Okay, so this is for chapter 20, carboxylic acid and their derivatives. So as usual, you will do the homework for those questions in the chapter. Right, so in this chapter, we're going to study carboxylic acid and their derivatives. Carboxylic acid are abundant in nature and found in a wide variety of synthetic pharmaceuticals also. And here are a few examples. The US produces over 2.5 million tons of acetic acid per year, which is primarily used to produce vinyl acetate. This one. Vinyl acetate is used in paint and adhesives. Carboxylic acid derivatives such as vinyl acetate are very common and play a central role in organic chemistry. Monocarboxylic acid are named with the suffix OIC acid, oic acid, example butanoic acid, and this is 5-hydroxy for dimethyl pentanoic acid. The carbon of the carboxylic acid moiety is assigned locant number 1. So number 1, 2, 3, 4, 5. When carboxylic acid group is attached to a ring, it is named as alkane carboxylic acid. So here example, this carboxylic functional group is attaching to the hexane, cyclohexane. Therefore, the name will be cyclohexane carboxylic acid. There are also many common names for the carboxylic acid: formic acid, acetic acid, propanoic acid, butyric acid, and benzoic acid. Dicarboxylic acid are named with the suffix dionic acid. Here is one example: pentadionic acid. Some carboxylic acid have common names: oxalic acid, malonic acid, succinic acid, and glutaric acid. Recall the carbonyl has trigonal planar geometry. The acid moiety is capable of strong hydrogen bonding, including hydrogen bonding between acid pairs. And here's one example. So this really have a pair of hydrogen bonding. As a result, carboxylic acid have a higher boiling point than alcohol. Recall carboxylic acid are weak acid. They exist as a carboxylate salt in the presence of base. For example, this acid in the presence of sodium hydroxide. So the hydroxide take the proton away, make the carboxylate salt and water. Carboxylate ion and in the suffix OATE. For example, benzoic acid will be the sodium benzoate. In water, carboxylic acid only dissociates slightly, that is, they are weak acid. And here is the equilibrium. So the pKa of most carboxylic acid is between 4 and 5, and benzoic acid pKa 4.19. Acetic acid pKa 4.76, and propanoic acid pKa 4.87. Compared to HCl or H2SO4, carboxylic acid are very weak acid. Compared to the alcohol, they are relatively acidic. And here's the comparison. Acetic acid pKa 4.76, and the pKa for ethanol is 16. Now we know the smaller the pKa, the stronger the acid. Recall the stability of the conjugate base carboxylate due to resonance. So the negative charge is delocalized over all the 3 atoms, so that will become more stable. Consider the equilibrium between carboxylic acid and carboxylate at physiological pH 7.3. The acid and the conjugate base acting as a buffer. Recall the Henderson-Hansel-Brock equation: pH equal to pKa plus log the concentration of the conjugate base divided by the concentration of the acid. At a physiological pH 7.3, the ratio of carboxylate ion and the corresponding carboxylic acid is 1,000 to 1. For example, pyruvic acid exists primarily as a pyruvate ion at a physiological pH, and here is the equilibrium again. So this acid, this is the native ion, is favored at physiological pH. This is basic. So therefore, the pH is higher than the pKa of those acids. Recoil electron withdrawing substituents have a greater effect on acidity. The stronger and or closer they are to the acidic proton, the stronger the acid. And here are let's compare them with the acetic acid. If we substitute some of those H on this measure by Cl, the more we substitute, the stronger the acid become. And also the far away the substituting like Cl away from the acid, and then the weaker the acid. Electron withdrawing group substituting affect benzoic acid as well. So let's say this substituting called Z and has the table pKa. The Z in this example is in the para location, and depend on the strength of the electron withdrawing of those substituent, and we can see the pKa getting larger and larger. The smallest pKa will be the nitro group in this location, which give us pKa 3.4. So this table is a review of method for preparing carboxylic acid. The first one we can see is the oxidation cleavage of alkyne. The triple bond can be break apart by using ozone and then work up, produce two parts of the acid. So that is covered in chapter 9, section 9. Oxidative cleavage will break a CC triple bond, forming two carboxylic acid. The second one is oxidation of primary alcohol. We covered that in chapter 12, section 10. And a variety of a strong oxidizing agent can be used to oxidize primary alcohol and produce a carboxylic acid. Here's the structure of primary alcohol. For example, we can use sodium dichromate in the presence of sulfuric acid, oxidize this alcohol to the carboxylic acid. We can also doing the oxidation of some of those alkyl benzene, as long as this carbon attaching to the benzene ring has at least one proton, we can oxidize and cutting off everything else and produce this benzoic acid. Two more reactions that produce carboxylic acid. One is the hydrolysis of nitrile. Nitrile has this functional group C2N triple bond. So acid catalyzes hydrolysis with heat, produces carboxylic acid. So this allow a two-step synthesis of carboxylic acid from alkyl halide. So for example, we have alkyl halide here. We then use SN2 reaction to produce this nitrile, then nitrile hydrolysis produces the carboxylic acid. So another reaction is carboxylation of Grignard reagent with carbon dioxide. So Grignard will have this alkyl group. In general, you will see the group will be R and MgBr. So this is the Grignard reagent. So this R has relatively negative charge, and so this has relative positive charge on the magnesium. So therefore, this can have this reaction, for example, with CO2 and adding one more carbon and produce this native ion. Then the native ion work up with acid, produce the final carboxylic acid. This gives us a second method to converting an alkyl halide into a carboxylic acid in a two-step synthesis. So we're starting with bromobenzene, use magnesium metal in solvent of diazo ether, produce this Grignard, then reacting with carbon dioxide work up with acid, produce benzoic acid. Carboxylic acid can be reduced to a primary alcohol with lithium aluminum hydride superlar. So this is the carboxyl functional group, and LAR is lithium aluminum hydride. We have to do two steps because that is a strong base. So first, without water, then use aqueous acid to produce the alcohol. LAR is a strong base, so it is deprotonates the carboxylic acid first and produces carboxylate ion. The carboxylate is reduced to an aldehyde with the this AlH3, and the aldehyde is reduced to the primary alcohol with aluminum hydride. Note the reduction of carboxylic acid involving a change in the oxidation state. So it's kind of here we have this carbon bonding to 3 oxygen because this double bond contains bonding to 2 oxygen, and the product only bonding, the carbon only bonding to 1 oxygen. There's also many reactions where carboxylic acid do not change the oxidation state if Z is a hetero atom. So in those kind of reactions, there's no change in oxidation state. And this actually will be a variety of carboxylic acid derivatives that we studied. Most common carboxylic acid derivatives are the acid halide, for example, chloride, and acid anhydride, ester, and amide. Any compound where carbon has 3 bonds to electronegative atoms is a carboxylic acid derivative. So therefore, this nitrile also carboxylic acid derivative. Acid halide and anhydride are relatively unstable and are not common in nature occurring compound. Ester and amide are abundant in nature. So for example, this is the ester, which is in the pineapple, and this ester, which is in banana. This ester is in pear. Proteins are comprised of repeating amide linkage, and many other compound features amide, including some natural sedative like melatonin. Here is the amide. To name an acid halide, replace IC acid with YL halide. Acetic acid become acetyl bromide. Benzoic acid become like a benzoyl chloride. If an acid halide group is connected to a ring, the suffix carboxylic acid are replaced by carbonyl halide. Cyclohexane carboxylic acid become cyclohexane carbonyl chloride. Acid anhydride are named by replacing acid with anhydride. Acetic acid will be acetic anhydride. Succinic acid and become succinic anhydride. Asymmetric anhydride are named by listing the acid alphabetical order followed by the anhydride. So here we have this anhydride come from the acetic acid, benzoic acid, alphabetically acidic benzoic anhydride. Esters are named by naming the alkyl group attached to the oxygen followed by the carboxylic acid name with the suffix ATE. Acetic acid, and we'll call if we replace this H by ester, so therefore become ester acetate. Malonic acid and can replace both H by alkyl if both of them are the same ester, so therefore diester malonate. Some rules apply. Same rule apply if the ester is connected to a ring. So here is the cyclohexane carboxylic acid, and here we'll call methyl cyclohexane carboxylate. Amide are named by replacing the suffix ic acid or oleic acid with amide, acetic acid, acetamide, benzoic acid, and benzamide. If amide group is connected to a ring, carboxylic acid is replaced by carboxyamide, cyclohexane carboxyamide. If the nitrogen atom of the amide group bears alkyl substituting, their names are placed at the beginning of the name with N as the locant. So here is the methyl on this nitrogen in this amide. The name is N-methyl acetamide, and we have two methyls, N-dimethyl acetamide. Nitrile are named by replacing the sulfuric acid or oleic acid with on nitrile. The acetic acid, acetonitrile, benzoic acid, benzonitrile. Carboxylic acid derivative are electrophilic at the carbonyl carbon, carbonyl carbon, carbonyl carbon, or carbonyl carbon, carbonyl carbon, carbonyl carbon. A relativity determined by induction, resonance, steric, and quality of the leaving group. So the relativity going from amide increase to ester, then increase to anhydride, then increase to halide. Halide is the most negative derivatives. Acyl chloride are the most negative derivative because in induction, the electronegative chlorine enhances the electrophilic character of the carbonyl carbon by withdrawing the electron away from the carbonyl group. Resonance, the chlorine does not significantly donating electron density to the carbonyl because if that do have this donating electron from the chlorine produce CCl double bond, but because the p orbital overlap required for this CCl double bond is not effective because of the size difference between the p orbital on the chlorine and the p orbital on the carbon. The net effect of the chlorine atom is to withdraw electron density, rendering the carbonyl group extremely electrophilic. Amide are the least reactive acid derivative. Examine the factors below to explain amide reactivity. First, induction, the nitrogen is less electronegative than chlorine or oxygen. Resonance, the nitrogen atom contribute significantly electron density to the carbonyl, as shown in this resonance structure. So this lone pair on the nitrogen can donating to the carbonyl, make the carbonyl carbon less positive. This overlap produces this double bond between carbon and nitrogen is effective because they are both in second period, so their size of the p orbital are similar. Aldehyde and ketone are also electrophilic, but they do not undergo substitution because if we think about this Z, the chloride and or like those another carbonyl in the anhydride or ester, so they are better leaving group. In aldehyde or ketone, so either the alkyl group are in ketone or the hydrogen in aldehyde, they are not a good leaving group. Carboxylic acid derivative under nucleophilic ester substitution. So here is you can think about those derivatives attacked by the nucleophile, then push out the group Z. Nucleophilic ester substitution, the general mechanism has two core steps. The first step is the nucleophilic attack, the nucleophile. The carbonyl group is attacked by the nucleophile, forming a tetrahedral intermediate. This tetrahedral intermediate, and loss of leaving group, subtracting the Z group. A leaving group is expelled, and the carbonyl group is reformed. Nucleophile attack the carbonyl tetrahedral intermediate form, then carbonyl reform. We are loss of leaving group. Each hydride or carbide generally cannot be expelled as leaving groups. Specific examples, let's say this chloride and can be attacked by methoxide. First produce this tetrahedral intermediate. The best leaving group is eliminated, carbonyl is reformed. So Cl one negative or chloride, the better leaving group than methoxide. So therefore we have this product with the ester. Understand the nucleophilic ester substitution is not an SN2 mechanism. So we can see the SN2 mechanism is concerted. That means even in the same time the nucleophile attack the carbon, the leaving group is reduced. So that is not a concerted process. Sometimes a proton transfer will be necessary in the mechanism under acidic condition. Negative charge rarely forms. Under basic condition, the positive charge rarely forms. All the participant chemical mechanism reactant intermediate leaving group should be consistent with the condition employed. Specific example where acidic conditions are used. Here we have this ester reacting with water in the acidic condition, produce carboxylic acid and alcohol. The first step will not be nucleophilic attack because negative charge the oxidant will not be produced under acidic condition. So therefore, we will see this this process. Under acidic conditions, the first step will be the protonation of the carbonyl. So protonation is generally always the first step in ester substitution mechanism under acidic condition. Nucleophilic attack on the protonated carbonyl makes much more sense under acidic condition. So now we have this tetrahedral intermediate, and the activation energy is slower, so therefore the process is faster. Once we have that, then we can do the nucleophilic attack. Now, under the basic condition, the carbonyl is not protonated first. The strong nucleophile will attack first, and so here's the reaction. When amine is the nucleophile, it will attack the carbonyl first without the carbonyl being protonated first. A tetrahedral intermediate with plus and negative charge forms here. Just be sure to avoid drawing an intermediate with two charges of the same type when drawing those ester substitution mechanism. Proton transfer are utilized in mechanism to remain consistent with condition employed under acidic conditions. Up to 3 proton transfer are necessary in the mechanism. So this is the general step. Whether the conditions are acidic, neutral, or basic, you will have to decide where a proton transfer occurs in the mechanism. Consider the mechanism for the following reaction. We have this hydrolysis of chloride produce the acid. The conditions are not acidic, the carbonyl is not protonated first. So therefore, we'll see the nucleophilic attack from water to the carbonyl carbon produce tetrahedral intermediate, and then loss of leaving group and the reform of the carbonyl and will produce this intermediate. So then this another proton transfer produces the final acid. The leaving group does not require protonation in order to leave, but there is a proton transfer at the end. Consider the mechanism for the following reaction that was saw before. So this pattern is typical for reaction of acid halide. So we have no proton transfer, just nucleophilic attack, also leaving group, then proton transfer. So 3 steps. An acid chloride is synthesized from carboxylic acid using SOCl2. The mechanism is split into 2 parts. The first part is the conversion of OH into the leaving group. So here is the nucleophilic attack from the SOCl2. So the carbonyl double bond acting as a nucleophile attack the sulfur. Okay. So the carboxylic acid function as a nucleophile and attack the cyanide chloride. And then this leaving group is not the OH yet, so the leaving group is in this part, the chloride leave. A chloride ion is expelled at the leaving group. So then this chloride can abstract this proton, reform this carbonyl, and this part is a very good leaving group. Therefore, we can use the chloride attack this carbonyl carbon and expel out this SOCl one negative SO2Cl one negative ion, produce this halide. So the mechanism again it will be the nucleophilic attack of water to this halide and produce this intermediate. Then the leaving group here will be the chloride that abstract the proton, produce acid. But since HCl is a byproduct of hydrolysis, so we have to use some base to get rid of the HCl to make the reaction goes. So therefore, we usually, for this reaction, we usually use pyridine to neutralize the produced HCl. Acid chloride are reacted with an alcohol to make an ester. For example, here is an alcohol and has the chloride, acid chloride. Sterically hindered alcohol reacts more slowly, so the primary alcohol can be acylated selectively in the presence of a secondary alcohol. So here the secondary alcohol has a primary. We use this chloride in the pyridine. We only acylate. That means put this ethyl group on this OH, not on that OH. Acid chloride are used to synthesize amide, and we have this three type of amide. We can use ammonia, we can use amine, we can use different amine, but we have to use two equivalent. Pyridine is not used to mop up the HCl byproduct here. Instead, two equivalent of the amine are used. One for the nucleophilic attack and the other for the to neutralize the HCl produced. Acid chloride can also be reduced using NAR to form a primary alcohol. Here's one example using excess lithium aluminum hydride to get this primary alcohol. Note that acidic workup is necessary because we cannot put them two together. So here the mechanism, nucleophilic attack from the hydride. So the carbonyl group then reform and expel the chloride, and we produce this intermediate aldehyde. So then second time nucleophilic attack from the hydride, and then produce this tetrahedral intermediate. Protonation finally produce this alcohol. By using lithium tricarboxy aluminum hydride, here this structure, instead of NAR, the reduction can be stopped at aldehyde. This reagent is more selective and react with only acetic chloride faster than the aldehyde, so the aldehyde can be isolated. Acid chloride can be reacted with the Grignard reagent to form a tertiary alcohol. So we have this acid chloride use excessive Grignard reagent RMGBr, then work up, produce this tertiary alcohol. The mechanism is analogous to reduction using NAR. So here is Grignard nucleophile attack the carbonyl carbon, tetrahedral intermediate, and then reform the carbonyl, expel the chloride at the leaving group. Another Grignard attack and produce another tetrahedral intermediate, and then protonate this, produce the final tertiary alcohol. The Gilman reagent, lithium dialkyl cuprate, can be used instead of the Grignard. So this is an example of a genetic formula of lithium dialkyl cuprate. The Gilman reagent adds only once to the acetic chloride to form a ketone. So we kind of waste one of the methyl or the alkyl group. And this figure 20.9 illustrates the reactions of acid chloride as we discussed. Is a very good summary. So committing those two memories. And so how we prepare the acid chloride from the acid, okay, how can we reduce back into the acid? Once we have this acid chloride, we can go through many of those reactions. Anhydride can be synthesized by excessive heating of carboxylic acid. For example, acetic acid heat up to 800 degrees Celsius produce acetic anhydride, and this only works for acetic acid. To make anhydride, most acid cannot survive extremely temperature like this. We have to use some other way. A more practical synthesis requires an acid chloride reacted with a carboxylate nucleophile. So that's how we produce anhydride. Mechanism, for example, we can take a carboxylic acid react with, the acid chloride react with the carboxylate and produce the tetrahedral intermediate, and reform the carbonyl, expel the chloride, produce the anhydride. Given that both contain good leaving groups, the reactivity of anhydride is analogous to acid chloride. So here the acid chloride has the anhydride. Chloride is a good leaving group, then this also a good leaving group. But it is not necessary to use pyridine with anhydride because a strong acid is not generated as a byproduct. So this figure 20.10 shows how anhydride can undergo many reactions analogous to those of acid chloride. And again here, first, how we converting between acid and anhydride. After we get anhydride, we can have this quite a few reactions. Acid anhydride is often used to acetylate an amine or an alcohol to make an ester or an amide. So acetylate, which means you adding this part onto some of those compounds. We can take that acetic anhydride reacting with alcohol produce ester, or acetic anhydride reacting with amine to produce amide. Acetic anhydride is used commercially to synthesize aspirin and Tylenol. Now here is using the acetic anhydride to make aspirin, and this second reaction is using acetic anhydride with p-aminophenol to produce acetaminophen or the Tylenol. Ester can be prepared by SN2 reaction of carboxylate with an alkyl halide. So here is an acid, and so first using base produce the carboxylate, then reacting with alkyl halide, for example, methyl iodide, to produce this ester. Okay, so sodium hydroxide is used to deprotonate the carboxylic acid and yield carboxylate in the first step. Fischer esterification combine a carboxylic acid and an alcohol using an acid catalyst. That is the acidic condition. So here the acid has alcohol, produces ester. Acidic condition, the mechanism is consistent with one that occurs under acidic condition. Next slide, this slide. So there are quite a few steps. First step is proton transfer, because under acidic condition, proton needs this carbonyl group render it more electrophilic. And once we have this protonated carbonyl, then the alcohol function as a nucleophile attack the carbonyl carbon, produces this tetrahedral intermediate, then the proton transfer, the positive charge is removed we are deprotonation, and then we are protonating the alcohol again, and so we'll have this positively charged intermediate, another reform of the carbonyl expel water at the leaving group. And then we deprotonate this protonated carbonyl, produce the final ester. The mechanism for future esterification reaction is supported by an isotope labeling experiment. So here we are labeling this oxidant in this alcohol. Then we examine where is this labeled oxidant. We found it's on the ester. So we know this reaction in the last slide is true. Some step is true. So the future esterification is an equilibrating process. Water must be removed to favor the formation of the ester, and also adding more reactant. So adding more reactant remove the product to start this other principle. Ester can also be prepared by treating an acid chloride with an alcohol. So in section 20.8, acid chloride, alcohol, and in this case we'll use pyridine to neutralize the produced HCl. Ester can undergo hydrolysis under basic conditions for the saponification, and we use selenium hydroxide, for example, then work up to produce the acid. Acid work up is necessary to obtain the neutral carboxy acid product. Otherwise, we have the carboxylate. Saponification mechanism, basic conditions, and the first step is nucleophilic attack. Hydroxide function as a nucleophile, attack the carbonyl group. Loss of leaving group. So the carbonyl group is reformed by expelling an alkoxide ion at the leaving group. The proton transfer again, the carboxylic acid is deprotonated by alkoxide, generate the carboxylate. And the mechanism is what one were expected under acidic condition, and is the reverse of Fischer esterification. So the ester hydrolysis mechanism under the acidic condition, it will be protonating the carbonyl oxygen first. So then we have the nucleophilic attack from water. Then we deprotonate the positive ion. The positive charge is removed via deprotonation. And then we will protonate this oxygen from the alcohol, and then the carbonyl reform to expel the alcohol. The final is another proton transfer to render this acid. Ester can also undergo aminolysis to form amide. So has ester using amine to produce amide. The overall equilibrium favors amide formation. Amide are more stable, less reactive than ester. The synthetic utility is limited because the process is slow. It is more efficient to make an amide from the acid chloride in section 20.8. Ester can be reduced using reagent such as lithium aluminum hydride. We had to use excess LAR to reduce the ester to primary alcohol. So two equivalent of reducing agent are required. Two alcohol are produced. Mechanism is analogous to reduction of acid halide with LAR. Here's the mechanism. And so we will have the first step is the nucleophilic attack. LAR delivers a hydride which attack the carbonyl carbon, produce this tetrahedral intermediate. The carbonyl group is reformed by expelling mesoxide ion at the leaving group. So this is mesoxide. So produce this intermediate aldehyde. The carbonyl group is attacked again by hydride, generate an alkoxide. This alkoxide This alkoxide is protonated to produce the final alcohol. Reduction of an ester can be stopped at the aldehyde by using diol instead of LAR at a lower temperature. So here the diol, which is standing for diisobutyl diisobutyl aluminum hydride. For example, this is the ester using the diol, then work up, produce this aldehyde. Ester can also react with the Grignard reagent to form a tertiary alcohol. We have to use two equivalent of the Grignard. So this is the Grignard reagent. Then work up with water to add the 2R group on this carbonyl carbon. This reaction and mechanism is analogous to the reaction of an acid halide with Grignard reagent. So there are the steps. First is the nucleophilic attack from the Grignard alkyl group. The carbonyl group are reformed by expel the alkoxide. Produce this intermediate ketone or aldehyde. So the carbonyl group is attacked again by the Grignard, generate another alkoxide. Alkoxide protonated by the solvent and water to produce this tertiary alcohol. Amide can be made from any of the carboxylic acid derivative already discussed. So has amide, the least active derivative. We can make that from chloride, acid chloride, acid anhydride, or ester. So here the diagram. The most popular way to make an amide is from an acid chloride and the corresponding amine. We need two equivalent of amine. Remember, two equivalent of the amine are necessary when full equivalent is used to neutralize the HCl byproduct from the reaction. The other one is used to adding onto the acid chloride. Amide can be hydrolyzed with acid, and here is amide, and under heat with acid produce acid. This reaction is slow and requires high temperature. The products are favored at equilibrium because an H3 group is protonated and not capable of acting as a nucleophile in the reverse reaction. The mechanism is proton transfer or protonation of the carbonyl. The second step is the nucleophilic attack from water. Produce this tetrahedral intermediate. Another proton transfer. So remove the proton, then this positive charge is removed. Then we'll have another proton transfer to protonate this nitrogen. Then reform the carbonyl to expel the NH3. Deprotonate the protonated carbonyl and finally produce this acid. Amide can also be hydrolyzed under basic condition. And here is under basic condition, we have, for example, sodium hydroxide and with heat, then work up to produce acid. The base catalyzed hydrolysis is even slower than when acid conditions are used. The mechanism is analogous to base catalyzed hydrolysis of an ester. So you can see the first the attack of the carbonyl by the hydroxide, and then reform of the carbonyl expel this amide. So that's why it's slow, because amide is not a good leaving group. The NH2 minus is not a good leaving group. Once that is expelled out, so that will take the H away from this acid, produce this oxidate. Amide are reduced to the corresponding amine with LAR. So we reduce this carbonyl carbon to the C2. The mechanism is quite different from the other we have seen in this chapter. The carbonyl group is completely removed while the nitrogen remains bonded to the molecule. Recall when a primary or secondary alkyl halide is treated with cyanide ion, the cyanide ion acts as a nucleophile in an SN2 reaction to produce this nitrile. Nitrile can also be made by dehydration of a primary amide using a variety of reagents, including SOCl2. So here's the primary amide. Use SOCl2, it is reduced to nitrile. The primary amide dehydration mechanism. So we have this the carbonyl, the amide function as a nucleophile and attack the cyanide chloride, produce this intermediate. Then the 1Cl as a leaving group, so lost chloride. Then another proton transfer deprotonate this this nitrogen atom, and then we produce this intermediate. So then another proton transfer to take another H away from this nitrogen atom and expel this leaving group, produces nitrile. Nitrile can be hydrolyzed under basic conditions. So this nitrile under acidic condition produces amide, and then this amide can be converted into the acid. So the nitrile is first hydrolyzed to a primary amide, then further hydrolyzed to the carboxylic acid. And under basic condition, the nitrile hydrolysis is this few steps. The first step is the nucleophilic attack by the hydroxide. So we produce this intermediate. So the negative charge on the nitrogen atom is removed via protonation and produce this intermediate. Then the hydroxide function as a base and remove a proton, forming a resonance stabilized intermediate. So then the final step, another proton transfer, produce this amide. Nitrile are hydrolyzed to carboxylic acid under acidic condition, and here is the reaction. Again, acidic workup is necessary to obtain the carboxylic acid because basic condition otherwise yield a carboxylate. The mechanism is starting by proton transfer. Protonation of the nitrile group render it more electrophilic. So then the water can acting as a nucleophile attack the carbon. Proton transfer again, the positive charge is removed from the oxygen by deprotonation. Then we can protonate the nitrogen and produce this resonance stabilized intermediate. We can take the proton away from oxygen, produce the final amide. Nitrile can also react with Grignard to form ketone, and here is the reaction. So we can think of this nitrile, the nitrogen is spelled out to produce this ketone. After the nitrile react with Grignard, water is added to form imine, which is then hydrolyzed with excess of H3O+ to form the ketone. Similar to how carboxylic acid can be converted to alcohol using LAR, nitrile can also be converted to primary amine. So we use excessive LAR and we will reduce this nitrile to amine. when design and synthesis stick with the same strategy as with any synthesis discussed earlier. First, is there a change in the carbon skeleton? Secondly, is there a change in the functional group? There are many new functional group transformations in this chapter. See the next slide. And we can see these functional group transformations. Starting with the acid on the top, we can converting acid into this acid chloride, anhydride, ester, amine, and nitrile. Then from those, we can interconverting between chloride and those derivatives, or converting into like aldehyde or alcohols. So there are two kinds of CC bond forming reaction covered in this chapter. We study how to use, for example, Grignard, and we can see here are some of those examples. It is useful to recall a CC bond forming reaction from section 13.12, which move the functional group by two atoms. So for example, here we have this carbon atom is functionalized. That means we have this, it carries the Br group. So we can use this few steps, use magnesium, then use some alkoxide, then we were adding 2 more carbon, more than 2 more carbon. This R can also have some carbon here. So therefore, we shifted this from this functionalized carbon to this carbon. And so when forming new carbon-carbon bond, it is critical to install functional group in the proper location. Recall the C2O double bond stretching is a prominent peak in IR spectra. So the carbonyl stretching frequency can also be used to identify the functional group it is part of by using the frequency wave number. The typical carbonyl group for the acid chloride is about 1800, and then anhydride getting a little lower or higher to signal. Then we have this acid, and then ester, then the ketones and amide. Recall that the conjugated carbonyl signal appears at lower wave numbers, about 40 wave number less than the saturated carbonyl. The oasis stretch of an acid gives a very broad peak, to all the way from 2500 to 3300 wave number. So the CN triple bond stretch appears around 2200 wave number. The carbonyl carbon 13 peak appears around 160, 180 ppm. Nitrile C13 peak appears around 115 to 130 ppm. The proton peak for carboxylic acid proton appears around 12 ppm. That's really down the field. For this practice the number and the chemical shift of all the carbon 13 peak for the molecule below, predict the number chemical shift and the multiplicity and integration of all the proton peak in the molecule below. So here, the first is predicting how many peak and the chemical shift for all the carbon here, and all the carbon will be different, will give different signals. And here are the results. The H, we label those H like HA, HB, C, D, E, F, and so here are the signals. Okay, so this is the end of chapter